In this video, we're going to take some class notes on the topic of ionic compounds. In the previous video, we discussed several aspects of ionic compounds, and we're going to go into some more detail during these notes. Ionic compounds typically involve a metal atom with low electronegativity. So it has a low electronegativity value. So the metal atom with a low electronegativity value, losing valence electrons to a non-metal atom with a high electronegativity value. Typically, this is what takes place when you are dealing with ionic compounds. The metal atom is going to be losing electrons to the non-metal atom. The whole reason that this happens, the reason that a metal atom is going to give its valence electrons to the non-metal atom is because the metal atom has a low electronegativity value, a low attraction for electrons. Due to a large difference in electronegativity values, the electrons are transferred from the metal atom to the nonmetal atom. The whole reason this happens is because the metal atom has a low electronegativity value and the nonmetal has a high electronegativity value. The metal atom changes into a cation. And remember that a cation is a positive ion. You're losing negative electrons, so you're turning into a negative ion. And the non-metal atom changes into an anion. And an anion is a negative ion. We talked about in the previous class the resulting structure, and the resulting structure is that positive and negative repeating pattern of the ions. But what I want to focus on here is this idea of electronegativity, and not just electronegativity, but the electronegativity difference chart. So it's not just the value of the electronegativity, it's the difference in electronegativity of the atoms that are involved in the bonding of the ions. So the value, the electronegativity difference chart is going to look like this. We're going to start over on the left-hand side. And remember, we're not looking at electronegativity. We are looking at the electronegativity difference between the two atoms. So we're looking at the electronegativity of one atom as compared to another atom. So here, the values can range from 0 up to 0.5, and then from 1.6, and these are designations of the difference in electronegativity between two atoms. Let that get back into focus there. So the electronegativity difference between the two atoms. One of your reference pages that you have is the electronegativity chart. So what I want to do is I want to look at an example of two atoms and how they bond together. Before doing that, I'm going to put some designations up here. And I'm going to put the term ionic here. I'm going to put some lines in here, and we're going to put a question mark in this area. And then up here, we haven't talked about this yet, but it will be called a polar covalent bond. And over here, we haven't talked about this either. It will be a pure covalent bond. So polar covalent and pure covalent. So in looking at the type of bond that can exist between one atom and another atom, let's look at this first example. And the first example I'm going to look at is Na with Cl. So the first thing that I'm going to do when looking at Na and Cl, I'm going to recognize that Na has a certain attraction for electrons, and it's 0.93. So Na has an attraction of 0.93, and Cl has an attraction, an electronegativity value of 3.16. We are not looking at their values of electronegativity, but specifically we're looking at the difference in electronegativity. So when looking at the difference in electronegativity, we take our 3.16 and we subtract it from 0.93. And the difference in electronegativity is 2.23. This is the electronegativity difference. Because the difference is greater than 2.0, that means the type of bond it's going to make is an ionic bond, which means that the metal atom with a low electronegativity of 0.93 is going to lose its valence electrons to the nonmetal atom with a high electronegativity, which is in this case 3.16. So the way that we would show that is we would show Na with one valence electron in column 1A, Cl with 7 valence electrons because of 7A, and we would show the electron being transferred, being moved. Why is it moving from Na to Cl? Because Na has a low attraction for electrons. Cl has a strong attraction for electrons. So the electron leaves, it transfers over. We end up with an Na plus and a Cl minus, which makes the formula NaCl, and it's designated as an ionic compound. During the last video, we looked at that structure of the repeating pattern of positive and negative ions. Now, in this case, we can also notice that Na is on the left side of the periodic table, designated as a metal. Cl is on the right side of the periodic table, designated as a nonmetal, and that's typically what happens. Typically, you have a metal atom and a nonmetal atom. That's generally the case. So now let's take a look at this example of Na with I. For Na with I, for Na and I, Na is 0.93. We've already looked Na up, 0.93 on my electronegativity chart. I is 2.66. So when we look at the electronegativity difference between Na and I take 2.66 and I take the difference of 0.93 and I get 1.73. 1.73 is the electronegativity difference. So now the question becomes, the difference isn't really that big. If it's bigger than 2.0, then it's ionic. But it's in this area where the atoms, even though the atoms have a different strength and electronegativity, it's not so big. It's kind of in this middle area. So what we have to determine is, in this area, is it an ionic compound where they are going to transfer the valence electrons, transfer of electrons, or is it going to move to a polar covalent, which we haven't learned yet? Well, what's the rule that we're going to use? Here's the rule. If we are in this area right here, here's the rule that we're going to use. If it's a metal and nonmetal, then we will call it ionic. If the difference in electronegativity is in this area and we're dealing with a metal and a nonmetal, we call it ionic. If it's a nonmetal and nonmetal, we call it polar covalent. And I apologize, I should have given you some more room there. So now, let's take a look. Where are we? Well, Na is on the metal side. I is on the non-metal side. The stair-step line is not listed here, but you can see that I would be on the right side. So, because metal and non-metal, we say it's ionic, and we would have Na and I, and because it's ionic, we would be transferring the electrons over, making an Na plus and an I minus with NaI. Because it's in this middle section, but we are still a metal and a non-metal, we would call it ionic. Now, let's look at one more example. What if we had this formula, PF3? Well, for PF3, when we look up P, it has an electronegativity value of 2.19. And F has an electronegativity value of 3.98. So the difference between the 3.98 and the 2.19 come out to be 1.79. An electronegativity difference of 1.79. But here's the difference. P is a non-metal. It's to the right of that stair-step line. F is a non-metal. So since both are non-metals, we will call this bond non-metal and non-metal. We will call this bond a polar covalent bond. We don't know how to show bonding of a polar covalent bond yet. That'll be in a subsequent unit. Right now, what we're doing is we're looking at the bonding of two atoms, where one atom is a metal that has a low electronegativity. The other atom is a non-metal that has a high electronegativity. Due to the large difference in electronegativity values, the electrons are transferred. They're moved from one atom to another. The metal atom changes into a positive ion. The non-metal changes into a negative ion, and that's what causes them to attract. Their difference in electronegativity is so big that the electrons move from one atom to another. What we will find in subsequent units is down here, the electronegativity values are so close together, neither one of the atoms is strong enough to take the other atom's electrons away, so they share electrons. In this area, they share electrons, but right now we're dealing with ionic, where their electronegativity is so different. One atom is so much stronger than the other atom, it takes the other atom's electrons away. If we're in this zone of, well, is one atom really strong enough to take the electrons away? Or is it so close that they're going to share electrons? When you're in this zone, if it's a metal and a non-metal, we will say the electrons are transferred and call it ionic. But if it's two non-metals, then we say that they will share electrons. I hope this helps with understanding ionic compounds and how it relates to the electronegativity difference of the two atoms involved.